Okay, hi folks. I want to start by thanking Jerry and Frank for organizing this meeting, despite all the hardship that was involved in that. I hope this is still going to be a great opportunity for us to exchange ideas and techniques and help each other do more with colony weight monitoring and other forms of colony monitoring. So the title of my talk today is Landscape Scale Flow and Dearth Monitoring, a robust method for messy data. This is work that I did while a postdoc at Penn State, though I have since finished that postdoc and I'm doing another postdoc at the University of Würzburg in Germany. But this work is from my time at Penn State. I want to start by acknowledging some folks who were involved with it. First and foremost, Don Schump was my collaborating my research collaborator and also the beekeeper who provided the hives and the infrastructure to do this project, and it would not have been at all possible without him. And Christina Grosinger was my postdoc mentor at Penn State. This work was funded by a USDA NIFA postdoctoral fellowship and an Apis Valentis research award. So I'm going to start by introducing you to a place, because this is a project that is very much grounded in a place, and in fact, it is a place that I am very much personally grounded in. This is my hometown of Philadelphia, Pennsylvania. And I show you these pictures to illustrate two things. First, I want to demonstrate just how much variation is encompassed by the word urban that we assign to landscapes. These are all images from urban Philadelphia, and they vary as widely as this abandoned cemetery in the top left to the downtown skyline in the center. The other thing these pictures illustrate, though, are my research sites. At the center of each of these pictures, you can't see it, but there's an apiary with honeybee colonies that I used in the research that I'm going to present. Here's a more schematic view of how my sites were set up. This is a map of Philadelphia with a land use layer, so you can get a sense for what the landscape is like and how it varies. And the goal of this research was to study how honeybees interact with urban landscapes in terms of foraging. How do they find food in landscapes that are both so urban and so variably urban? What does this mean for both how much and when food is available and exactly what kind of food is available? So both the how much and the what questions of floral resources for honeybees. And the main work I'm presenting today involves the weight monitoring of these colonies, though we did also collect pollen samples and honey samples and use DNA metabarcoding to identify the plants that those samples came from. So I'll mention that briefly, but I would encourage you to look at our paper for a fuller discussion of that. But for weight monitoring, we used broodminder hive scales. This is the generation of broodminder that we were using. And I realize there's a newer generation out now. I haven't had a chance to try it yet, but this is the kind we used, where it sits under one edge of the hive. And while it is not illustrated in this particular photo, which happens to be the nicest photo I have of our setup, but it does not show that we, in general, use the technique that Rich and Teo recommend for setting up broodminders, where you have the back end of the colony sitting on a piece of angle iron to create a more consistent fulcrum for stabilizing the distribution of weight onto the scales. In this particular site, we had to deal with a sloped concrete slab, which served the same purpose as the angle iron, but it was exceptional. For anybody who's worked with weight data, though, this is not just a broodminder issue. This is, I think, common across virtually all the weight monitoring platforms we have available. You have various forms of noise that you have to deal with, and there are at least two kinds of data messes that we have to deal with in order to analyze these data. First, you have these random misreadings. They just happen sometimes. I don't know why. And it's not really that big of a deal because it doesn't affect your interpretation of the pattern. You can still see what's going on. You can imagine what it would look like in the absence of these one-off errors. More problematic, though, are the weight artifacts that are actually reflect real events, but events that have nothing to do with the natural growth of the colony. These are things like honey harvest or supering. And Under ideal circumstances, you would take really thorough notes and you would know exactly when a given management intervention happened, and you would have before and after weight, and you could, with zero uncertainty, just subtract that change and reconstruct your data. But this is real life. If you've ever done field studies with honeybees, you know that that kind of perfect note-taking and that kind of stuff just doesn't end up happening, at least not consistently. And this was a working apicultural business we were in here. This is so these were not just research colonies. These were Don's beekeeping operation colonies. So we have lots of these artifacts, and I don't have a nice clean way of just making them go away. So I had to build an analytical workflow that would handle both these kinds of data problems and give us data that we can interpret with respect to our main question, which is what the pattern of nectar flows and dearths is in Philadelphia. Here's an overview of this workflow, and it's described complete with the code that is behind it in our paper, which just came out a couple months ago. I'll show you at the end. I want to give you a quick overview and then zoom in on each of these steps. So we'll start with, we have our raw data in the top left, and then we take the first order difference, which turns those level shift outliers, those management artifacts, into single one-off outliers. Then we can filter those, reintegrate them, downsample to just midnight readings, and then we're going to fit a smooth function to these, and I'll explain that in a minute. But let's zoom in on these steps. So our raw data looks something like this. We have problems of the sort that I described. And this is real data. This is not simulated data. This is just one of my hives for one of my sites. And so the first thing we do is take the first order difference, which is, it's the difference between consecutive measurements. So instead of a time series of absolute weights, you have a time series of weight change. It's conceptually the same as taking the first derivative, except this is a numerical rather than an analytical approach. I didn't do any calculus, I assure you. I just subtracted some consecutive measurements. And when you do that, you get something that looks like this. And as I said, those tricky level shift outliers arising from management artifacts get turned into these simple additive outliers, these one-off outliers, and that makes them pretty easy to deal with. So we can come through and we can filter out any reading that reflects a weight difference greater than some value that we consider reasonable. And the way I determine this value is by looking at histograms of these weight change time series. And it was clear that the normal variation was between positive and negative 2.5 kilograms. And so I went through, and any weight change that was in excess of that, I set to 0. So it's as though that weight change didn't happen, whether that's a single one-off weight change or if it's a level shift weight change due to honey harvest or something. Then when you get rid of those, you can zoom in on the data that remains, and it's clearly a lot cleaner. We can start to see we might be able to work with this. Then we can just undo the differencing step and reintegrate our data into absolute weights. So we get something like this. We've stitched our time series back together. So instead of looking like this, it looks like this. And this is something closer to what the natural pattern of the colony would have been apart from those artifacts. And then, because I'm not interested in hourly level variation, I'm really just interested in daily variation in the context of this project, and I don't care to explain the extra variation in the hourly measurements. I downsampled to just the midnight readings. And then I also, because I did not trust that the absolute weight measurements meant the same thing at every site, because scales that sit under just one end of a hive are sensitive to weight distribution, and the different setups across different hives and sites and little nuances that I did not measure or could not account for. The scales are sensitive enough to things like that I did not want to bank on having accurate absolute weight measures. So I converted all my weight measures to z-scores. I z-normalized them, which means you set the mean to 0 and the standard deviation to 1. And that makes them more directly comparable with each other. In a situation where you are confident in your absolute weight readings, you would not have to do that. But for the purposes of inferring flow and dearth periods, you don't need to be confident in your absolute weights. You just need to be confident in the direction of your weight. And that's what makes this method robust to the uncertainties we have about the weight data. And finally, I mentioned some kind of a smoothing function to get an overall picture of how weight changes through time. So this is what happens when you have 36 colonies, and you want you can plot them all here, but you have this big cloud of points, and you can kind of see patterns in it, but it's a little hard to interpret. And what you might want to do is fit some kind of a smooth function to this that captures the overall signal that's common across these colonies, that describes the study region that you're working in. Or you might want to describe the shape of individual colonies, or perhaps multiple colonies within a site. But in any case, you want something smoother than just the raw point data here. And the solution I found to this is called generalized additive modeling. I won't go into it in detail here, but it's essentially a statistical approach that enables you to model processes that are smooth and curvy rather than being basically straight lines. Classical statistics likes to assume things are straight lines, and if they're not really straight lines, you try to make them as close to being a straight line as possible, and then you model it as if it were a straight line. But there's nothing like a straight line about the fluctuation in colony weight data. So we need to embrace that, the wiggliness, the non-linearity of those data, and generalized additive models are a great way to do it. They're implemented in the R package MGCB. I'd be happy to talk more about this. I don't want to get too deep into it right now, but a good place to start is this paper by Eric Peterson et al. The modeling that I did for this project was very much based on the techniques that they present in this paper. And when you do that, you can fit a smooth function like this that allows you to capture the overall effect of the patterns across multiple hives, or even just a smooth generalization of a pattern in a single hive. But then I took it a step further to improve the visualization. So in this graph, you see 4 panels. Each one is divided into a top and a bottom half. So the first 3 are individual sites, and the third one is a global model made from all the sites. Each of these sites includes 3 different colonies. And you see you note that the data are standardized. See that they have a mean 0, and they vary around that mean. But in the tops of each panels, you have the integrated GAM smooth for the 3 colonies at that given site, or in the case of the global model, for all the colonies across all my sites. Then in the bottom half of each panel, you have, I once again took a first order difference, but instead of taking it from the raw time series data, I took it from this nice, smooth, generalized additive fit. And that enables you to create these area plots where when the curve is above 0, that represents weight gain. And when the curve dips below 0, that represents weight loss. And I think that's a very intuitive way to visualize these weight curves when your question is about when and how long nectar flows and dearth periods occur. And so these are the global models for the 2 years of data that I collected from Philadelphia in 2017 and 2018. And note that in 2017, I did not collect for as long a period, so it's a bit chopped off at either end. But you can see that there's a lot of consistency across these 2 years. We have these 2 strong spring flows in May and June, and then in July, weight gain levels off and hangs around 0. And then in August, every colony in my study lost weight. This was the most universal pattern in my data was weight loss in August, which is interesting in that beekeepers have always talked about a summer dearth, but to see it so clearly illustrated in empirical data is good. It's a good confirmation of what we have anecdotally talked about in the beekeeping community. And then there's this short nectar flow that happens in September. When I give this talk, I usually give it to a group of knowing beekeepers, and I say, okay, what do you all think this nectar flow in September was? And we say, 1, 2, 3, say it, and everyone gets ready to say goldenrod, and just as everyone's saying goldenrod, I say Japanese knotweed, because this ain't Ohio. This is Philadelphia. We don't have goldenrod, but we do have Japanese knotweed. And so instead of having a big aster flow this time of year, we have knotweed, and we have also things like English ivy and these very exotic assortment of flora that you would not necessarily expect. But then after that short flow in September, that's about it for the rest of the foraging season. Now, these patterns are meaningful to me from a basic ecological perspective. My questions are really not so much about honeybees in particular in this study, but about the floral resources, using the honeybees to measure them. And so from these patterns, you can get an overall sense for how, under urban land management, floral resources are patterned in time and potentially in space if you look at differences across sites. But also from an applied apicultural perspective, this is clearly very useful if you're trying to time nectar, or if you're trying to time honey harvest or supplemental feeding. You would want to do so with respect to your expectations of when flows and dearths would happen. And finally, on this project, I mentioned that I did pollen analysis. I don't want to dwell on it too much, but there's also structure in the plants that were contributing to these flows, or the ones that were mitigating the dearths, the ones that were still coming in during dearth periods. And I encourage you to check out our paper to see more of that. But one pattern that stands out is that the early spring flows are really attributable largely to trees, and then perhaps to clover in June. With herbaceous plants becoming more and more important as you get toward the middle of the year. And then interestingly, the trees you see here during the August samples, those are mainly a plant called Devil's Walking Stick, which is an invasive understory plant. That is, it's Aurelia alata, the Latin name, and it's extremely common in parts of Philadelphia, and that becomes the main resource for honeybees during that August dearth period, interestingly. And then also interestingly, I encourage you to read the discussion of this in the paper, but the fall foraging landscape is just absolutely dominated by woody vines, especially clematis and English ivy, heterohelix. And I think that is a uniquely urban phenomenon to see that dominance of these exotic woody vines. This is the paper that I've been referring to. It just came out a few months ago. I encourage you to look at it. This was very much a labor of love for me. I hope you enjoy reading it, and I hope that you find it useful both in your beekeeping, if you're a beekeeper, or in your research, if you're interested in research applications of these techniques. Or if you happen to be a Philadelphian and you're really interested in Philly like I am, then this is also a bit of a homage to my hometown. But in a sudden change of direction, I want to take this opportunity to present a problem that I have encountered with a totally different kind of monitoring, but it's still Hive monitoring, and so I trust it still falls within the purview of this meeting. This gentleman in the middle of the screen here is, of course, none other than Carl von Frisch, of dance analysis fame. And you can learn some really cool things about honeybees and their floral resources by mapping the spatial patterns of their foraging. And this has been done especially in recent years with the renaissance of dance analysis methods by Maggie Cuvillon and Roger Schuch. And it's very promising as a technique for looking at how resources are distributed in space. But as anyone who has attempted this before can tell you, setting up and managing observation hives is a ton of work. And even more work is recording and decoding all those dances. And so if you wanted to do something like I did in Philly, but with dance analysis, which, as it happens, I did want to do in Philly with dance analysis, you'd have to essentially replicate Carl von Frisch for as many sites as you have, so that you can have somebody sitting in front of each of those hives, recording data simultaneously and decoding it. This will require an army of well-trained field assistants, because, of course, I cannot be at all these locations simultaneously. So what to do? Well, invented a device. Invented is too strong a word. I put together devices other people invented in a slightly new way. And I gave it the somewhat cheesy name Carl von Pi, because this consists of a Raspberry Pi computer, which for those of you in the audience on like the tech development side of colony monitoring, you'll know exactly what a Raspberry Pi is. For those of you who immediately think of a baked good, a Raspberry Pi computer is a small, simple computer. To be fair, I didn't know what a Raspberry Pi was until somewhat recently. It's a very small computer that has no visual interface or anything, but you can plug stuff into it. And then by plugging, one of the things you can plug into it is a camera like this. And so what you can do is set up your combination of a Raspberry Pi and a camera like this, and you can program it to record the videos of your bees at whatever interval you want. So in my case, I was interested in recording 5-minute videos every hour between the hours of 9 a.m. and 4 p.m. 7 days a week. And it'll just go on and do that. And you can synchronize your recording in this way across as many sites as you have. And this setup costs about $75. It's a cheap computer, it's a cheap camera, and then there's some other cheap stuff you have to get to plug it in and everything. But for $75 per setup, you can automatically record data in a very standardized way. There still remains the challenge of decoding it, of course. This is not an automated decoding technique, though Roger Schurch at Virginia Tech is making progress on that front for the automated decoding. So I'm hopeful that that will be a possibility in the future. But there are some unresolved challenges here, and I want to submit this to this group to see if I can get any feedback for how this could be made better. So there are two problems. They're related. The first is that when you're filming on, when you're recording video on an observation hive, the glare off the glass of the hive is a really serious problem, especially when you're working in a place like the Natural History Museum that I was working in here, or the public library that I was working in another instance, where I can't tell people to turn off the lights. So I imagine there has to be some way of reducing glare. This is not my field at all, but perhaps some kind of filter, some kind of coating. Tell me your thoughts. I think we can solve this problem. And then I think some kind of standardization of lighting is important, but I think we can use infrared lighting to avoid A, messing with the bees, and B, hopefully minimizing reflection off the glass. Because these cameras can record in infrared, it's as simple as just turning off the infrared filter that would otherwise filter out the infrared light. So I think this is a solvable problem. And once we fix that, these record high quality video. And as I said, for a fraction of the cost of a single camcorder, you can get something that will record without you being there, which is the real key here. Incidentally, you could also very easily set this up to live stream to your outlet of choice. So I'm going to stop there. This is my email address. I'm going to give you my Gmail account, because if you have an idea 3 years from now, and I will have no doubt finished another postdoc by then, institutional emails are hard to keep up with. This one should be pretty stable. So if you have ideas or feedback, I welcome them. And with that, I think I'll close. Thank you for your time.